Hi guys. So I'm recording at home today, and I've been having some issues with making it pretty clear up on the whiteboard, and I have to show you some stuff on my calculator. So I'm going to use the dot cam for this video. This is 2.5, which is just dealing with functions. Specifically, the first thing we're going to talk about is called the fundamental theorem of algebra. So what the fundamental theorem of algebra does, specifically in what I wrote down for you, is that it refines our statement for the number of zeros that are possible. This being that specifically in the complex number system, we get to improve how many zeros are possible. If you remember when we talked about in the last section or last couple of sections when we've been talking about how many real zeros there are, we said that it was up to n amount of zeros. So there could be n number of zeros or less. Again, that's where n is the highest degree. So in the complex number system, and now that we've introduced what a complex number is, we actually can now state the following, and that is that there are exactly n zeros in an nth degree polynomial. So again, let's say that the highest exponent is 5. You will have exactly 5 zeros to that polynomial. So something to keep in mind is these zeros are both real, imaginary, and you're also going to come across multiplicities. Okay, so that's when there's two zeros that are the same number. You'll see those imaginary and then the real zeros. So in this chapter, in this section specifically, we're going to say how many or name or find all the zeros of the function. Before we may have been saying just find the real zeros or just find the multiplicities. Now we're saying we want to know what all of them are. So looking at some examples, this first one is just saying in the function f of x, that is x squared minus 6x plus 9. We want to first just state that since the highest exponent is 2, there has to be exactly 2 zeros. So let's go ahead and find those 2 zeros then. Again, finding zeros in specifically even just a quadratic function is going to be done by factoring. So we want to find two numbers that multiply to positive 9 but add to negative 6. Those two numbers would be negative 3 and negative 3. So we write out these two binomials, x minus 3 times x minus 3. This would be a multiplicity. We're going to have x equals 3, as I did not mean this little dashed line. That was supposed to be there. X equals 3 is 1, and x equals 3 is the second one. So two zeros, both the exact same zero, but that's okay because they're still exactly 2. Second example. In the function f of x equals x cubed plus 4x. We want to state that it will have exactly 3 zeros here. Now let's go ahead and find those. Again, by factoring, I always like to start by, is there a greatest common factor that I can pull out? Considering the fact that both of these functions have a variable of x, I can go ahead and pull that variable out, leaving me with x squared plus 4. Again, the thought process behind factoring out a greatest common factor would be if we factor out an x, it's the same thing as dividing each of those terms by x. X cubed divided by x gives me x squared. 4x divided by x gives me just 4. We're going to go ahead and set this equal to 0 because we know we're trying to find the zeros. I cannot factor x squared plus 4 any further. The first thought is that I have that difference of squares formula and method of factoring, but considering that this is not a negative, then it's not a difference of squares. Although x squared is a perfect square and 4 is a perfect square, I still can't use that method because it's not a subtraction. And if I start thinking about, okay, I want to multiply two numbers to positive 4 that give me 0. That's because there's no middle term. There's no x term in here, so that term must be 0. Since I can't find two numbers that multiply to positive 4 but add to 0, that gives me that this function is not factorable. So instead, I go ahead and I set each of these parts, the first part and the second part, equal to 0 separately. We always know from here, I just try to solve for x. The first one's already done for us. The second one would be x squared equals negative 4. Square root both sides. That would be x equals plus or minus. If I'm taking the square root of a negative, let's keep in mind from 2.4, what I do is pull out an I and make the inside positive. So I can take this just a step further, and that would be simplifying to x equals plus or minus I. And we can even actually write this, not the I first. This would be x equals plus or minus. I know that the square root of 4 is 2, so it would be 2i. So my 3 zeros in total would be 0 for the first one, positive 2i, and negative 2i. Okay, so I stated I should have 3 zeros. I do, in fact, have 3 zeros. An important note is since some zeros can be imaginary, you may not be able to see them all in the graph. So specifically what I'm talking about is imaginary zeros. Imaginary zeros are not visible on a real XY graph. So imaginary numbers exist on the imaginary system, but on the real system they don't exist. So we will not actually see them. We know they're there based on factoring and finding them algebraically, but we just can't see them on a graph. So if I wanted to go ahead and find all zeros of the function, f of x equals x to the 5th plus x cubed plus 2x squared minus 12x plus 8. First thing I'm going to do is I'm going to graph it. So I put it into my calculator because I want to see, where do I visually see zeros? That's where I'm going to start off first. So if I plop that into, here we go. If I put it into my calculator, I want to start visually saying, I see a 0 right here. That's at negative 2. So x equals negative 2 is a 0 that I'm seeing. I will test these, but I'm seeing it. And if you also wanted to do that second calc, you can go ahead and just ensure that, oh, where did it go? Oh, let's do that one again. There we go. So just to ensure that I am seeing that this 0 is at negative 2, I can go ahead and do the second calc in my calculator to calculate that 0. Remember, whenever you're faced with something to the e to the negative power, that is just going to round down to 0. So it is, in fact, a 0 at that point. So I need to bring that back. The other 0 that I'm seeing is right here at positive 1. So remember, multiplicities can happen. When they do happen, it's because you touched the x-axis but did not truly cross it. So let's go ahead and zoom in here. I want to make sure that I know what's actually happening. Oh, that is not the kind of zoom that I wanted. Let's go back to zoom standard. And now let's go ahead and zoom in. So again, I'm zooming in to try to see, am I in fact touching or am I truly crossing this x-axis? So as you can see, this was the first 0 we found over here, so that was negative 2. And now when this function is coming down, it's just barely touching the x-axis, bouncing back off and going up. So since we are not crossing the x-axis, it is a multiplicity at that point. So at 1, I have 2 zeros. So keeping in mind this function is a fifth degree function, so I should have 5 total zeros. I'm seeing 3 total real zeros. So what I do from here is I start in on my synthetic division. So remember last time we used synthetic division to claim whether or not a factor was a zero? This time we're going to use it to help us factor this function out using the zeros that we know are zeros to get down to a point that we can continue factoring it ourselves and then find those last 2 zeros. All right, so these are the 3 that we're going to have to test. So we're going to just start out with -2, keeping in mind this is an x equals -2. So I've already solved for x, so I'm not taking the opposite. So when I set up my synthetic division, I keep it a -2 on the outside. That's my divisor, because I've already gone through that process of solving for x. I check for any 0 placeholders. I skip from a 5 to a 3, meaning I'm skipping 0x to the 4th. So I do need a 0 placeholder in there. But then I go from 3 to 2, 2 to 1, 1 to nothing. So that's the only 0 placeholder that I need. Go ahead and take the coefficient of 1, 0, 1, 2, -12, and +8. We start by dropping that first term down. So it's a 1. 1 times -2 is -2. That's a really wonky negative sign. 0 plus -2 is -2. Now we can go ahead and multiply -2 times -2, that's +4. Add straight down. 1 plus 4 is 5. 5 times -2, -10. Add straight down. -8. -8 times -2, +16. Add straight down, +4. One last time, 4 times -2 is -8. Add that straight down and we get 0. 0 is what we needed. That meant that yes, -2 is a 0. But what have I factored out so far? I've factored out x plus 2. Okay, since this is a -2, I've factored out the factor x plus 2, right? We want to write these the opposite way. So one factor is x plus 2, the other one's x minus 1, and x minus 1. By the time I get done with all of my synthetic divisions, I will have factored out all 3 of those factors. So we continue on with the second synthetic division, setting up 1 on the outside of this one. And we use what's left over from that first synthetic division as my numbers up top. So 1, -2, 5, -8, and 4. We leave the 0 out because we don't need it. Drop down 1. 1 times 1 is 1. -2 plus 1 is -1. -1 times +1, -1. Add those straight down, you get 4. 4 times +1 is 4. -8 plus +4, -4. Multiply -4 times 1. You get -4. Add straight down and you get 0. So yes, x minus 1 is a 0. Very last one. We again have to test this very last one out here. So bring down the 1, -1, 4, and -4. Okay, bring down everything from that time before. Drop down the 1. 1 times 1, 1. We get 0. 0 times 1 is 0. Add that up, +4. Multiply those together again, +4, and we get 0. So it's important to note what I've factored out so far is x plus 2, x minus 1, x minus 1. What's left over comes from the bottom of the synthetic division. We know my final term is the remainder to r. This last term's a constant. This is my x, and this is my x squared. You can barely see the little square there. So what I have to do is, one, I know that I'm left with x squared plus 4. That's the last part that hasn't been factored out. So 1 0 comes from this factor, 1 comes from this, 1 comes from this. That means 2 have to come from my very last factor. Because remember, we need 5 total. 1, 2, 3, 4, 5. So these are all set equal to 0. I have to take this last factor, come over here, set it equal to 0, and solve for x. That will be x squared equals negative 4. Again, we've seen the ending like this before. I'm taking the square root of both sides. X equals, square root of a negative turns into ni, and then the square root of 4 is positive 2. So plus or minus 2, I specifically. So all my zeros can be listed out as negative 2, positive 1, positive 1, positive 2i, and negative 2i. Exactly 5 zeros. 1, 2, 3, 4, 5. It was a 5th degree polynomial, so that's exactly how it should have happened. Okay, so these are very much longer problems, but it's putting together everything that we've learned so far into one big problem. The very last thing that I want to go over with you is conjugate pairs when talking about zeros of a function. So when we talk about complex numbers, we talked about them in the form of a plus bi, where a is the real part and bi is the imaginary. So if a plus bi is a zero of a function, then so is a minus bi. So what this is saying is whenever I'm trying to find the polynomial containing certain zeros, if I am given any singular imaginary number, I have to understand that, sorry, I was just fixing the I. I have to understand that if there's one, there's a second one, because they come in conjugate pairs, because we find them by taking a square root of a negative number. When we take the square root, we take that plus or minus symbol. So this is the positive version. I have to also be able to note that negative 3i is also going to be a zero then. Okay, so I have to be smart enough to put that in. So let's go ahead and finish out this problem then. So whenever we're finding the zeros, that basically means that we first have to take each of these and set them equal to x. So we take x equals 3i, x equals negative 1, x equals negative 1, x equals negative 3i. Second step is getting them each set equal to 0. So that would be subtracting over 3i, so x minus 3i, adding over 1, x plus 1 equals 0, x plus 1 equals 0, and adding over the 3i. So x plus 3i equals 0. I take each of these binomials and set them all together to multiply together. But I'm going to keep my imaginary 2 next to each other. So I'll have x minus 3i times x plus 3i times x plus 1 times x plus 1. So I like to multiply my two imaginary parts together and then whatever real portions are together first. This is because I generally am going to get, for the most part, all of my imaginaries will cancel out before I have to multiply them with my real part. So it's just an easier process for me. So let's multiply this out. X times x, x squared, x times positive 3i, positive 3ix. It doesn't matter the specific way you write this, but just keeping that all together. And then negative 3i times x, negative 3ix, negative 3i times positive 3i, negative 9i squared. Okay, so that's the product of multiplying these two together. Now I'm going to take these two binomials, lastly, multiplied together. X times x, x squared, x times 1, that's x. 1 times x, that's x. And 1 times 1 is simply just 1. So sorry, I got distracted. So let's go ahead and start putting together our like terms. In this case, those two cancel out because they're conjugates of each other. Positive version, negative version. So that leaves me with x squared minus 9, but I'm replacing I squared always with negative 1. So then on this side, x squared by itself. Then I have plus 2x plus 1. Again, x squared, negative 9 times positive 1 is, or negative 9 times negative 1 is positive 9, all multiplied by x squared plus 2x plus 1. So now I just do that distribution process again. X times x, x squared times x squared is x to the 4th. X squared times 2x is 2x cubed. X squared times 1, just x squared. 9 times x squared, 9x squared. 9 times 2x plus 18x. 9 times 1 is 9. So one final process of combining like terms. The only two I have to combine are these two x squareds, giving me a final polynomial of x to the 4th plus 2x cubed plus 10x squared plus 18x plus 9. And I'll throw an f of x out in front because this is my final polynomial. And that would be the answer to this one. Okay, a little bit longer video, but I wanted to make sure we got through everything in 2.5 and got a good full explanation of it. So if you have any questions, please just let me know.